Hi everybody, welcome back. Today we're going to cover some new characteristics of a histogram beyond what we did last time, so we'll dive right in. Once again, a histogram shows us the distribution or the spread, essentially, of a variable and how a variable shows up in a set of subjects. So people finish some survey, we'll say, on some continuous variable, and then a histogram shows us how that variable laid out. That's great because that starts to let us assess for patterns in the data. For example, one of the obvious things that we can look for is kind of where's the rough middle of those data, or what is the average of the data. Now we'll talk about a mathematical way to do that, of course, and assess the mean later. We'll do that later. But just visually, we can see a rough estimate of where the mean is, and or the average, and I can show you how that looks in just a second with a histogram. Additionally, it also shows us just how spread out those data are from each other, and it shows us the lowest value and the highest value. And so all of this is going to be very important, very useful as a rough kind of estimate of what the data are doing. So let's take a look at a histogram. So if this is a roughly bell-shaped distribution, or a histogram that has a bell-shaped curve, is what we usually refer to that as. It looks something like this, right? In theory, a bell-shaped curve is symmetrical down the middle like this, and it looks roughly like a bell. So kind of think of the Liberty Bell kind of thing. We talked about why this shape occurs last time, or at least theoretically why it should occur. Now, as I said, you could see some pretty obvious things here. So the average, if I were to say, what is the average here? Well, it's where most of the values occur and right around that most. Now, that's not necessarily the definition of average. We'll get to that later. But if I were to say, hey, what score best represents this data set, you would probably say right there in the middle, right, is the 100 score. And that's true, by the way, IQ has a mean of 100. So, and then if I were to go beyond that and say, well, what else can you tell me about the data? One thing you could tell me is that there were very few very low scores, and in this particular data set, we didn't have any scores below 40, didn't really have any scores much beyond 160 or 163, whatever that happens to be, 164. All right, and so you could start to tell me some things, and if somebody came up to you and said, hey, I got a score of 140 on the IQ exam. Just given this distribution, you could say, wow, that's relatively rare. It's high and it's relatively rare because look how relatively fewer people had that. The frequency is relatively low. So anyway, a histogram in and of itself is quite useful. And now we need to talk about some things that are different about the bell-shaped curve, or different from the bell-shaped curve, so that we have the language to understand what's going on here. So once again, a bell-shaped curve is theoretical, and in reality we usually don't see perfectly bell-shaped curves given our variables in nature, and that's because it may be sampling error, it may be just because of natural variations among the people on that variable, or it doesn't have to be people, but whatever it is we're measuring, right? So it's very unusual to find a perfectly bell-shaped curve, but just how much our particular distribution from real data deviates from a bell-shaped curve is something that we'll need to talk about and assess and be aware of as researchers and as people who are consumers of statistics. So we'll now talk about asymmetrical distributions very briefly, and we'll introduce the new term for that. We call this a skew when you have an asymmetrical distribution along the middle. In other words, it's asymmetrical along whatever middle axis there is. So we'll take a look at a couple of distributions that are askew or that are not symmetrical. Let's start here. This is a distribution with a positive skew. So let's explain why first that it's a positive skew. Of course, you'll recall that on the x-axis, it's just the law that as you go towards the right, the value of whatever is on the x-axis increases, and as you go to the left, it decreases, right? And at some point, once you find the y-axis, that's where it's zero, virtually always. Of course, sometimes you sort of abbreviate just for the chart's sake, right? But on a two-dimensional plane that you use in geometry, for example, or other math courses, and especially algebra, you'll find that as you go towards the right, that's an increase, and going towards the left is a decrease. So therefore, if the stretch of the distribution, if it's stretching more towards the positive end, that is an indication that this is a positive skew. That's what we call a positive skew. In other words, another way to think of this is there's more variability on the, or on the right side of the peak of the distribution. That's a positive skew by definition. There's more variability on this side of the peak than there is on this side of the peak, and therefore that's a positive skew by definition. So for example, this is pretty much the distribution of educational attainment in the United States. So I'll describe that briefly. What we find is that about 90% of people, somewhere around 90% of people in the United States, adults anyway, have at least a 12th grade education. They have completed high school, or they at least have a GED equivalency, something like that. It's quite unusual for people to not at least finish that if they're age appropriate to doing that. So in other words, once you're 18, by the time you're 25, virtually everybody has at least a GED. Now, of course, you do find some people to the left of that, right? Some people drop out at 9th grade or 10th grade or something. I've known some people who were like that, right? There's some famous actors. Did you know Jim Carrey never finished high school? Of course, that's in Canada. He was Canadian. I think he's a citizen now. That's why I said was. Anyway, so most people have a GED, and then you find fewer people have some college, but actually most people in the United States do have some college. It's something like 60%. And then getting an associate's degree is actually quite a bit less. And then it'll get fewer and fewer. In other words, you can see the frequency decreases as I move to the right over here. And so people who have a doctorate degree, that's something like 2 to 3% of the population. And so it gets very, very unusual. In other words, you see a lot more variability after a 12th grade education than you see before a 12th grade education. And by definition, that's a positive skew. Now we'll see an example of the opposite of that, or a negative skew. And this one's an interesting, you can see there's quite an interesting shape here as well. So I'll describe that in a minute. Now, of course, it's a negative skew by definition because it stretches towards the lower end, right? It's stretching towards the 0 on the x-axis. And this is the x-axis. So you can see as the week of pregnancy goes down, I'm seeing more and more variability on that left side of the peak. So by definition, this is what is called a negative skew. You could refer to this as a negatively skewed distribution. Okay. Now, of course, the reason that this occurs is there's more variability on the left side of the average, or the peak in this case, which is by definition the mode, but we'll get to that, than there is on the right side. And we see this in nature, of course, because this makes perfect sense. And by the way, I looked this up. There is some data that backs this up. The week that a baby is born in the pregnancy, right? Your average is about 40 weeks of being born, and then there's some variability around that. That's perfectly okay and natural. It's not anything scary. In fact, it's pretty normal for some babies to be born at 37 weeks of gestation, for example. And it's not unusual for some babies to be born after about 42 weeks, for example. And yet you start to see a lot fewer babies born as you go down in the weeks. So I think the world record is a baby born at roughly 20 weeks, 21 weeks maybe of gestation, and then surviving, by the way. And then doctors like to have, of course, babies stay in as long as possible until about 40 weeks. And then it's medically, of course, possible around 24 weeks is pretty good odds that the baby's going to live and going to survive after a birth. So anyway, you see it's very unusual. These are usually due to some kind of medical emergency, some kind of medical problem where a baby's born earlier and significantly earlier than sort of your average of 40 weeks. And then it gets very, very unusual, of course, after about 43 weeks. Nobody's putting up with that. Any doctor is going to be like, we need to get that baby out of there, because it starts to get very dangerous for especially the mother after about 43 weeks of gestation. So this is why we've got a negative skew. Again, is you've got a lot more variability on the left side of the average than you do on the right side. So by definition, a negative skew. Okay, so just a quick review of what we talked about is that if a distribution is not symmetrical, a histogram distribution specifically, is not symmetrical at the middle, or at least roughly the middle, then it is called skewed. And the skew can be to the right, which is called a positive skew, or to the left, which is a negative skew. All right. Okay, and so we do generally expect to see a symmetrical distribution, and in reality we never quite get a symmetrical distribution. But what we start to get concerned about is if it starts to vary significantly from normal. If it's especially skewed, we need to start to explain why that's going on, and if we can correct for that in some way, that's important. So a researcher really likes to see a normal distribution or something very close to it, relatively close to it. Yeah. Now, of course, in reality, there are some legitimate reasons that a distribution isn't symmetrical. What's important is that our statistical tests usually assume that we have a symmetrical distribution or relatively close to a symmetrical distribution. So this is the kind of thing we need to be keep an eye out for as researchers. And of course, we'll hopefully see that throughout the rest of these lectures. But that's it for now. Thank you very much, and I'll see you next time.